Hi, this is Wendy Lightheart. In this video we are going to learn how to multiply and simplify radical expressions. So the main rule that we're going to be using for multiplying and simplifying radicals is that if the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b is equivalent to the nth root of a times b. So this tells us that we can combine two radicals that are being multiplied together as long as they're both the same root, so the indices are the same. And when we combine them, we end up with a single radical with the same nth root, and the product of the radicand goes underneath the radical, or the product of the two radicands that you are multiplying together will go under that new radical. So we will use this equation from left to right when we're multiplying radicals. However, most of the time we're going to be using this rule to simplify radicals, and we'll actually be using this equation the opposite direction, where we'll have a single radical, and what we want to do is split it apart into two separate radicals so that we can simplify. Okay, let's look at a couple examples. So here's a couple examples where we're just multiplying radicals, so we'll be using that rule from left to right. And remember that the rule says that the indices have to be the same in order to use the rule. So for example 1a, notice that they're both fourth roots. So that means we can use that rule because the indices are the same. And for 1b, they're both fifth roots. So let's see how the rule will be used for these two examples. So for the first one, the fourth root of 6 times the fourth root of 11, according to the rule, we could rewrite that as the fourth root of 6 times 11. And of course, 6 times 11 is 66. Okay, so the fourth root of 6 times the fourth root of 11 is the same as the fourth root of 66. Now let's look at example B. Here we have the fifth root of 3x plus 2, times the fifth root of 3x plus 2 to the third. And the rule says that we can multiply those two radicands together and put that product underneath a single fifth root sign. And remember that if you're multiplying something times a binomial, like 3x plus 2, you must put that binomial in parentheses. So that's very important to remember. And of course we can combine these because we have this same base of 3x plus 2, and using the rules of exponents we would combine those into 3x plus 2 to the fourth power. So we end up with the fifth root of 3x plus 2 to the fourth power. Okay, now let's see how we can use that rule to simplify radicals. Now the idea here is we want to split this square root of 72 up into two separate radicals that are multiplied together using that rule. However, it's not going to be helpful unless one of those factors is a perfect square. So let's look at the perfect square starting with 2 squared, which is 4, all the way up to 10 squared, which is 100. So what we want to do is find perfect squares that are also a factor of 72. So if you divide 72 by 4, you get 18. So of course that is a factor of 72. And 9 goes into 72 8 times, so it's also a factor of 72 that's a perfect square. And if you try dividing 72 by 16, you'll see that it does not go in evenly, so it's not a factor of 72, and neither is 25. However, 36 goes into 72 2 times, so it is also a factor of 72. And 49 does not go into 72 evenly, neither does 64. And of course, once we get to perfect squares that are larger than 72, then obviously they're not going to be a factor. So we can stop at 64, and now we've found all the perfect squares that are also a factor of 72. And what we want to use is the largest factor, or the biggest factor of 72 that's a perfect square. So while we could use 4 or 9, The one that we need to use in order to simplify this completely is 36. So since 36 is the biggest factor of 72 that is also a perfect square, we're going to factor 72 into 36 times 2 and use that rule. So the rule says that if we have this square root of 36 times 2, we can rewrite this as the square root of 36 times the square root of 2. So we're just breaking it apart into two separate radicals that are multiplied together, which is what the rule says we can do. Now this is helpful because the square root of 36 can be simplified since it is a perfect square. So we go ahead and simplify the square root of 36. The square root of 36 is 6, so we end up with 6 times the square root of 2. So the square root of 72 is equal to 6 times the square root of 2. And this is considered simplified because there are no perfect square factors left underneath the radical sign. Okay, let's look at another example. This time we're going to look at a cube root. So instead of looking at perfect squares, we're going to consider perfect cubes. So if we start with 2 cubed, which is 8, then 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. So usually this is as many of the perfect squares you are expected to remember. And if we look at these perfect cubes, what we want to do is find the largest one that's a factor of 54. So 54, if we divide that by 8, you'll see that it does not go in evenly. However, 27 goes into 54 2 times, so it is a perfect cube that's also a factor of 54. And notice that we've already passed up. If we go up to 64, we've already passed up 54. So we can actually stop there. 27 is the only perfect cube that's a factor of 54, so of course it's the biggest one. And notice we also have a negative sign underneath the cube root, so remember that you can take an odd root of a negative number, and that's considered to be a real number. So what we want to do in that case is we always want to factor that negative out of the radical to be completely simplified. So when you're factoring out that perfect cube that you find, go ahead and make it a negative. So we're going to say since negative 27 is the biggest factor of negative 54, that is a perfect cube, and x to the 6 is a perfect cube also. Now why is that the case? Well, when you're looking at the variables, what you want to do is find one that has an exponent that is a multiple of your index. Okay, so if you remember how to rewrite this as rational with rational exponents, then x to the 6, if we take the cube root of x to the 6, that would be x to the 6 over 3 for our exponent, and 6 over 3 of course is 2. So that's what you're looking for, is numbers that are divisible by the index. And since 6 is divisible by 3, that makes x to the 6 a perfect cube. Now y has an exponent of 1, so 1 is not divisible by 3, and it's not large enough to be able to factor out a power of y that's has an exponent that's a multiple of 3. So we're going to leave the y alone. And so since negative 54 and x to the 6 are perfect cube factors of this radicand, we're going to factor them out. So we're going to we're just splitting apart the radicand right now into separate factors, where negative 27 is a perfect cube factor and x to the 6 is a perfect cube factor. And then the rule says that we can take the cube root of all of these factors separately. So we're going to take the cube root of negative 27 and the cube root of x to the 6. We're going to do those first because those are the perfect cubes. We want those results to go out front. And then the cube root of 2 times y, we're just going to keep that together into as one single radical. Okay, so now we're going to simplify the perfect cube roots. So if 27 is 3 cubed, that means the cube root of 27 is 3. And so the cube root of negative 27 would be negative 3. Now with the x to the 6th, remember we're just dividing the exponent by the index. So 6 divided by 3 would be 2. So the cube root of x to the 6th would be x squared. So now we have negative 3x squared times the cube root of 2y. And notice that there are no longer any perfect cube factors underneath the radical. And that's what we were looking for. So now this is simplified. Okay, let's look at one more example. This time we're going to look at a 4th root. And normally with even roots, if we have a variable under there, if x could possibly be negative, we'd have to worry about absolute value signs when we're simplifying. But we're going to assume that x is positive here, so we don't have to worry about that. So since this is a 4th root, we're going to be looking at perfect 4th powers. So here are the first 3 perfect 4th powers. So 16 is 2 to the 4th, 81 is 3 to the 4th, 256 is 4 to the 4th. You can see that these go up quite, they get large pretty quickly. So really you're not expected to know any 4th powers higher than that, but you can always obtain them by just taking the whole numbers. So the next one would be 5 to the 3rd power. So remember, we're looking for perfect 4th powers, because this is a 4th root, that are factors of 162. So if you divide 162 by 16, you'll see that it does not go in evenly, so that's not a factor. However, 81 goes into 162 2 times, so it is a perfect 4th power that's a factor of 162. And of course, 256 is larger than 162, so we don't even need to consider that number. So what we're going to do here is factor out the perfect 4th power of 81 from this radicand. But also when you look at the x, remember we want a perfect 4th power of x that we can factor out of here. So 14, of course, is not divisible by 4, so it's not a perfect 4th power. However, we want the largest perfect 4th power. So if you think about it, we want an exponent that's less than 14, but a multiple of 4. So the next multiple of 4 that's less than 14 would be 12. So x to the 12th would be a perfect 4th power. That is a factor of x to the 14th. So since 81 is the biggest factor of 162, that is a perfect 4th power. And x to the 12th is the biggest factor of x to the 14th, that is a perfect 4th power. We're going to factor them out. So the 162 gets split up into 81 times 2, and the x to the 14th gets split apart as x to the 12th times x squared. Remember, it needs to be x squared because these exponents have to add up to 14. So now we're ready to use the rule that says that we can take the 4th root of each of these factors separately. So we're going to take the 4th root of the perfect 4th powers first. So 81 and x to the 12th, we're going to take the 4th root of those first. And the 2 and the x squared, we're going to keep those underneath the 4th root sign because they're not perfect 4th powers. And now we can simplify our perfect 4th powers. So since 81 is 3 to the 4th power, that will simplify as a 3. And remember, for the variables, you're going to divide the exponent by the index. So 12 divided by 4 is 3. So we get x cubed from that. And the 4th root of 2x squared, of course, stays the same. So notice we don't have any perfect 4th power factors underneath the radicals, so this is considered completely simplified. And that's it for today.